Hi, everyone. This is Tianyin from UIUC. Today, I'm going to present our work on configuration testing. So technical work of configuration testing has been presented at OSDI and ESTA. So my plan for today is to tell some of the stories which explains where we come from, why we firmly believe in this direction, and what are our next steps. Hopefully, to stimulate deep discussions at a workshop. So I believe with the audience of this Confluent workshop, I don't need to motivate more about the importance of configuration management, especially from the site reliability perspective, right? So from my personal experience, there are two types of bad configuration changes which constantly cause serious production incidents. So first type is those bad configuration values, right? So essentially the values are bad, they are incorrect. They can be as simple as typos, and it can be as tricky as undefined values. And if we roll those bad configuration values to our production systems, our production has trouble. And the second types of bad configs are even more tricky because the configs themselves are not necessarily bad. And many times they are valid, right? But the valid configuration changes essentially trigger dormant bugs in production code by exposing some new code passes which may not well executed before. So as a research group, software and system reliability, we have been thinking really hard on how to detect those bad configs and prevent them from being deployed to production. So there are two papers from industry which inspire us and encourage us greatly. So the first is the CACM paper titled Fail at Scale. It articulates the importance of having proactive techniques to capture those bad configs during the continuous integration and the deployment process. And the second paper is SSP 2015 paper titled Holistic Configuration Management at Facebook. It provides a number of very valuable data points. For example, it shows that configurations are changed even more frequently than source code changes at Facebook, currently thousands of times a day. And 16% of the production incidents at Facebook were related to configuration management. Although the 16% number does not really look pretty, but interestingly, the authors actually use this number at the conference to showcase that Facebook were doing much better than the other companies. At the time, there were a number of failure studies published by industry, which typically have a much bigger number on configuration, typically more than 20% or even 30%. So my first project is to build an automatic tool called Specs to fuzz the configuration interface. Right, so the idea is to generate a diverse set of misconfigurations and see how the system are going to react to them. And if the system break, then we claim we find a bug. Certainly, we want to do completely random fuzzing. So we actually do something smarter. So given a piece of system program, we actually automatically generate those configuration constraints information by statically analyze the source code. And we use the constraint information to generate test inputs. For example, if we observe that the configuration value is used in an open system call, we kind of know this configuration is related to files, and we generate all kinds of weird files to exercise the system. The project is very successful in terms of results. We find more than 800 software flaws, if we don't want to call them bugs, and more than half of them have been confirmed or fixed by the corresponding developers. So after seeing that, the software can hardly anticipate and deal with all kinds of misconfigurations. Later, I worked on a project called Specs. Sorry, I worked on a project called PCheck to automatically generate configuration checking code. We call those checking code checkers. So the idea is cute. We try to emulate those runtime execution that will use configuration values, by the program, right? And we want to do this at the system's initialization time. So any misconfigurations that causing weird behavior and fail those execution can be detected at that time. So we can capture those potential failures caused by misconfigurations as early as possible. So the hope is that when we are trying to deploy those configuration changes, we can actually observe their consequences during like the rolling update or at the canary phase, right? Rather than like observing like their late manifestation failed production. So given a piece of code, like we can automatically generate the checking code, and we actually did like one step further to insert like the checking code and invoke them like in the bit code for C programs or byte code for Java programs. Again, like the project is a great academic success. The work received one of the best papers at OSDI 2016, and it also helped me to take a sabbatical at Facebook during 2017 to 2018. And when I like landed at Menlo Park, sitting in my office, actually I don't have office but a desk. So having the freedom of like deciding like what to do next, a natural idea is to productionize PCheck, right? As PCheck is such an awesome project. So ideally, like we can automatically generate all the checking code, which currently like require like the human engineers to write like manually. Certainly, like later when I look at some of the like the checking code like written by my colleagues at my team, we are actually like working on a very kind of complicated traffic management, like traffic engineering system. And some of the like I realized that like some of the checking code or like sometimes called validation code are very complicated, which like not too advanced for PCheck to generate. But still, I firmly believe that PCheck can generate very useful, although like basic checks, which capture some like immediate like crashing behavior. Certainly, like when we work on research, like we have to evaluate like or at least access the impact. So that time, like the question in front of me is like how many actually production incidents, at least at Facebook, PCheck could potentially prevent if I'm really working hard and push like the best version of PCheck. The answer is interestingly like indicated by the Facebook paper, like I mentioned before. Like in that paper, there's a table which categorizes different type of bad configs based on like the offending configuration change, right? So essentially called the offending configuration diff because it changes the diff. So there are type 1, type 2, and type 3. Type 1 problem is those common configuration errors. Type 3 are subtle configuration errors, and type 3 are valid configuration changes exposing code bugs. And the difference between type 1 and type 2 are decided like based on human-centric process. So essentially like the authors basically find like those offending diff, offending configuration diff, and presenting them in front of those engineers and asking them whether this is a misconfiguration or not. And there are configurations which are easy to spot, for example, typos, format issues, out of range values, things like that. And the engineers, like after looking at the diff, they can actually say, hey, this is actually a bad config. But there are like configuration diffs like which are very hard even for human to determine whether they are bad or good, right? Many of them like are syntactically like and semantically correct, and many of them don't really like lead to crashes, but causing like these very subtle issues like resource leak or like performance degradation, things like that. So if we still remember like how PCheck work, we will realize that like it can only target type 1 cases, right? Because what PCheck does is really like try to just run the code which will use the configuration and see whether they crash or not. If you still remember like the number 16% I mentioned earlier, we do the math, like it leads to like 6.7% of the production issues. Later, actually, I talked to my like Facebook colleagues and some of my mentors at Facebook. They actually tell me like even this number is quite legit. Like it's a very justifiable impact, especially thinking about the disastrous consequences of those bad configs. But from the academic perspective, like the number is not that big, right? And I guess that if I present those number in a paper and send the paper into some peer review conferences, and the reviewer probably like will say that like this number is too small. Also, like I later did like an analysis, like a time-based analysis on those production configuration issues to validate like those numbers, and the numbers are more or less the same. But one trend I find is that like type 1 cases are becoming smaller, and my prediction is like they will be less and less, simply because like the company has more mature tooling and better practices, right? So at the point like I feel that like, pushing hard like on this p-check direction is not that exciting, at least to me. Instead, like, I really want to work on the type 2 and type 3, like, kind of bad configs, because of which like, kind of excite me, because they are bigger in terms of percentage and also harder to deal with. And at the time, like, there is no technique which can effectively, like, kind of detect, like, those type of, like, kind of bad configs. So I want to work on that. So the team I was working at, we used Keanu Reeves to name our team. So like, my profile was Keanu Reeves. So what are the fundamental challenges of these two types of bad configs? So for the type 2 problems, like, really, like, it's tricky that, like, those errors, like, they are mostly syntactically and semantically correct. And many of them are undocumented, or like, even unspecified, like, in terms of, like, the formal specifications. And many of them, like, they are bad configs just because, like, the code doesn't like them, right? There are some constraints, like, in the code, like, which basically, like, will break, like, under those configs. And also, like, many of them, they just don't like, causing, like, these immediate, like, kind of crashing behavior. And as I mentioned, like, resource leak, performance issues, bad load balancing issues are very tricky to even observe. And for the type 3 issues, like, the reasons are even more fundamental, because the root causes are just outside the configuration, but in the code, right? They are essentially code bugs triggered by the configuration changes. So any tools which only look at the configuration alone won't be able to find, like, those issues. So for type 2 issues, like, what we really need is to just check, like, the program behavior under those changed configuration, under the configuration we want to deploy to production, right? And I don't believe in, like, techniques to just codify, like, every single trivial, like, kind of code constraint, because remember that, like, the code is also changed rapidly, right? It's going to be very costly and, like, untenable. And for type 3, like, what we need is a method to test a code under the changed configuration, right? To test a code under the configuration you want to put in production. So essentially, what I'm looking for is some testing technique, which for every configuration change, it can test the change together with the code under the program context, right? And at the point, like, I guess some of you may think, like, almost every, like, company invests so much resource and, like, time, like, on all kinds of, like, software testing techniques, and why we need yet another one, right? So the fundamental issue is that, like, the production configurations are often not covered in test environment, although, like, we invest so much testing, like, kind of stuff, including unit testing, integration testing, and this and that. But the production environment is really, like, what we want to protect, right? Because it actually, like, help us to serve customers and make money. And essentially, like, in production environment, like, the system code is, like, run under the production configuration. And as we have seen, like, the production configuration are changed, like, continuously. So we look at, like, all kinds of, like, kind of tests or test cases in the test, like, developers write in, like, many of the open source code. And what we realize is that, like, those tests, they're using, like, they are not have a way to use those production configurations. Instead, most of them, like, using the default configuration or some of the hard-coded test configurations. And this discrepancy, like, really causing problems, because although, like, we spent extensive, like, efforts on testing, but the configuration, like, in the testing phase, like, may not really cover, like, the production configuration, right? So essentially, we are not really, like, kind of effective or efficient in consolidate our testing, like, kind of efforts to protect, like, the production environment. And the basic idea of C-test is exactly to connect, like, the production configurations to the software test, so that, like, we can focus, like, on the testing, focus the testing, like, on the production environment, and we're making sure, like, the code under the production is tested. All right. But when we look at, like, how the tests are written today, like, we just realize that, like, we cannot just directly reuse those existing software tests for, like, this purpose. And at this point, like, we present, like, a new type of test we call, like, C-test, stand for, like, configuration tests. So essentially, like, a configuration test is a software test parameterized by configuration parameters, right? run by like instantiating input configuration parameters with the concrete configuration values, essentially the values you are going to deploy. And since like C-test is like using software testing techniques, it checks like the program behavior against like the configuration to be deployed, so it can detect both type 2 and type 3 bad configurations. And we design like C-test for like continuous integration and deployment process. We make C-test which can be run like to test like a single configuration diff, and we design like test selection algorithms to only run a small subset of C-test relevant to the changed configurations. And last but not least, we later realized that like the C-test can be directly like generated from like existing software test. And this turns out to be extremely powerful because all the mature software projects already have so many tests. And since we can actually like transform those tests into C-test, we just get like a huge amount of like power to just like test those configuration changes. So let me just show you like some real concrete C-tests that can actually like deal with those hard problems as I promised. All right, so the first C-test can detect like bugs exposed by the valid configurations. The examples like are all like C-tests we generated like from existing like test suites of the open source code, and like also like the examples I show you like they are using like those bad configs which are actually causing like production issues before. So in this first example, so C-test is generated from a Hadoop test. So it's like testing Hadoop code, Hadoop configurations, right? So test logic is fairly simple. Like it first initialize a configuration object and pass the object into a server and use a server to call like to test basically like the server's authorization service. And as I mentioned, like different from traditional software test, in C-test like the configuration is instantiated like using like the actual like configuration you want to deploy, right? And in this example, the configuration diff has like this one change which changed like the value of this authorized parameter from false to true to enable this authorization service, right? And if we do that, like then like a new code path will be run because like this piece of code will be enabled, right? Because this branch prediction will be true. And in this example, like this piece of code has a bug, right? And if we change this configuration, then like the production Hadoop will fail its authorization service, and no like client can actually even getting like any passing any like authorization. It's a very serious issue, and this example is a real example, a real failure example. And you can see like if we run this C-test against like this config change, then we can detect the problem and preventing like this bad config be rolled to production. And the second example is from HBase, and it's also like generated from the HBase test. And similar as the previous one, we first initialize a configuration object, pass the object into a scheduler, and using scheduler to dispatch tasks, right? And the testing code, like the test code has assertion to assert like on the scheduling time. So we use this test like to test like a configuration diff. Again, like we instantiate like this config using this real configuration value, and this diff basically like change this factor configuration from 0.1 to 2, right? And in fact, like this is a misconfiguration because 2 is out of range value. The value is supposed to be between 0 to 1. And if we roll this to production, HBase will be very slow. And again, like this is a real failure case. The tricky thing about this misconfiguration is it's really hard to like detect because like it's undocumented first. Second, like in the HBase code, like there is no single line saying like this factor is bad. All right. So if you put it to like value here, HBase won't have any like abnormal behavior. The one throw exception, but just being slow. And interestingly, like this C-test, which is generated from the original test suite, can actually capture this bad config because it has assertion like here, and this assertion encode an environment of this scheduling behavior, which basically says that like the scheduling behavior should not change even like with different like factor values. All right, the factor is followed balancing, so it should always like have a deterministic like scheduling behavior, like here. And again, if we actually run a C-test ahead of time, it will just detect this bad config and preventing it from being deployed. And I hope at this point, you see some of the power of C-test. And we design some test selection algorithms for each given configuration diff, so that we only need to rerun a subset of C-test that exercise the changed configuration parameters rather than run every single one. I hope I have a time to explain this example to you, but essentially what I want to show to you is that in this very simple example, only 50% of the test needs to be run, because the other tests don't really touch the changed configuration. And we currently integrate Maven in our C-test framework, and it's also very straightforward to integrate other test runners such as Gradle, Bazel, and Buck, or any test runner you like. So as I mentioned, C-test can be transformed from existing test, and it can reuse those very well-engineered test logic and oracles, and this is extremely powerful. It sounds like a black magic, but if we think a little bit clearly, it's actually quite intuitive, right? Because what essentially a software test does is to exercise the code behavior, and what C-test does is to exercise the code behavior under the production configuration, right? So as long as there is a test which actually have generic test logic, which test the code under different configurations and have some assertions on to kind of check the invariants or other properties, then this test can be actually transformed into a C-test, right? Certainly, the challenge is that there are tests which are not written in such a generic way, right? And there are tests which making assumptions in other configurations of the code, and what we really need is to just identify those assumptions or those piece of test code, and we have quite effective heuristics to do that in an automatic way. So essentially, transform existing software test into C-test takes 3 steps. The first 2 steps are more about hacking the configuration APIs, so that we can instrument the API to know which test exercise which parameters, and we can feed the configuration we want to deploy to the test, so that they can run on the configurations we care, right? And step 3 are more fundamental. It try to identify and respect those explicit and implicit test assumptions on configs. And I hope I have a time to just explain to you the details about how to generate C-tests from existing tests, but I don't think I have. And I'm more than happy to explain this to you during the workshop time. And the code and data sets are all open sourced. If you're interested, take a look, and we are more than happy to help you if you have questions. And we apply the methodology onto 5 cloud systems, and we in total generated more than 7,000 C-tests for the selected configuration parameters. So we did a quite extensive evaluation on the effectiveness of C-test in capturing those bad configs. We did 3 things. First, we tried to see we collected 64 real world kind of failures caused by configurations, and we want to see whether those offending configuration changes can be actually detected by the C-test if we run this ahead of time. And second, we want to see whether C-test can detect diverse type of misconfigurations. We use specs to generate many different misconfiguration values, and we also apply the C-test to public Docker images and see whether C-test can find new kind of misconfigurations in the wild. So let me just focus on the first evaluation in this presentation. So again, we actually collected 64 configuration-induced failures, and we categorized them into those which are caused by bugs exposed by the configuration changes, essentially the type 3 issues I mentioned, and also erroneous values, essentially type 1 and type 2 issues I mentioned. We don't really differentiate the 2. And we can see that we run C-tests, 2 set of C-tests. The first is directly generated from the existing testing suite, and also the second set we also rewrite some of the assertions to make them more generic. And we find like for the bugs, we can detect most of them. We actually compare like our C test with like some the other like testing technique, mainly spell check and the P check. And spell check is mainly like type checking tool. And not surprisingly, like they cannot find any of these issues because simply like the configurations here are correct, and those tools are like looking for misconfigurations. And even for the erroneous values, we find that we outperform those like tools, especially like for spell check. Like if we find like if we only like do type checking, it's very limited because many of the bad configs which causing production issues, they are not simple type errors. And overall, like we find if we do C test, we outperform like existing like kind of misconfiguration detection techniques. So certainly, like C test has limitations. First of all, like any testing techniques, it heavily rely on the quality of the tests, right? So either like we have to write like a high quality test, or we have to have high quality test like already, so that like we can transform them like into C test. And some of our like generation heuristics, which essentially like try to determine like those test assumptions are not sound or complete. So it may have false positives and false negatives, but we actually like didn't even observe like false positive like empirically. Like it's quite fairly like effective. So one fundamental issue we realize like is that like C tests actually do not like fully like close a gap between the test environment and the production environment, right? It's to make a very solid step by ensure that like the piece of code is running like under the same production configuration, both in the production and in the test. But there are other factors which like causing like the problems, like the difference essentially. For example, the workload, the input, and also like the data sets. And we are thinking really hard how to just close the gap as much as possible. And if you have like great ideas, I'm more than happy to talk to you like at the workshop. So what's next? We are currently working on C-test prioritization and reduction with a goal of like just improving the efficiency of running C-test. So the prioritization basically like make it faster to find like the bad config. So the work is actually published at ISTA this year and received a distinguished paper award from SIGSOFT. And the reduction goal is to try to like skip redundant like test run as much as possible. So we are also working on a project to try to unify traditional regression test and the C test. So the current form of like C test assume no code changes, right? Only configuration changes because it actually focuses on testing the configuration diffs. So the question like we are asking ourselves is that can we actually apply the C test principle to code diffs so that like we can test the code changes under the production configurations. And if we do that, like these selection, prioritization, reduction all needs to be changed. So as a junior faculty, like I'm extremely lucky to have many great like mentors. And one of my mentors is Professor Darko Marinov at UIUC, and he is a very senior software testing professor. And among many of the things like he did for me, like he always asked me those very blunt, tough questions, like just to push me think harder and hopefully smarter. And one of the questions like Darko like kind of continuously like kind of asking me is what prevents C tests from being deployed tomorrow, right? And honestly, I don't have a definite answer at this moment because from my perspective, C tests are ready. We have the test infrastructure already. We have abundant like testing code in mature software projects, and we know how to transform those test code into C tests already. So if you have any thoughts, suggestions, especially concerns about C tests, I would love to hear from you and discuss with you. All right, that's all I have, and thank you very much. And I hope to see you at the workshop.